Before getting started, let me just mention what is the Oden Institute for those of you who are not aware of it. So actually, we do have an institute in many ways similar to IPAM here at UT Austin. It's called the Oden Institute for Computational Engineering and Sciences. So this is basically a permanent institute that is almost like a standard university department, except that we don't have undergraduates. We only have a graduate program. We have approximately 50 core faculty that have a split appointment between this institute and a department. And let's say the connective tissue is the fact that we are all doing some computational research from sciences to engineering. So just copy-pasted a couple of annual reports here just to show that there is work going on from condensed matter to biochemistry to planetary earth sciences to aerospace engineering. So the common thread is that everybody is doing either applied mathematics or high performance computing in a way or another. And hopefully this could be one of the starting points for more collaborations in the future between the Oden and the IPAM. So about electron-phonon interactions, I imagine that many of you are not familiar with this topic. So what I decided to do is to give a very brief introduction on where we see them. Then I will go over some of the methods and discuss some of the calculations we've been doing during the past few years. So this is our first example, just to connect a little bit to experiments. So the figure on the left is just a pretty schematic from this work by the group of Andras Stich at EPFL, where they realized one of the first transistors made of a two-dimensional material that's molybdenum sulfide. And when you have a system like that, the quantity of interest for engineers is how fast electrons or holes can travel in this channel when you apply an electric field. So this quantity, so this property is quantified by a quantity called the mobility of carriers. And this is a plot of experimentally measured mobilities in this material. The point I want to make is that this property, this quantity, as you can see, it decreases with temperature quite significantly. And this decrease is one of the most obvious manifestations of electron-phonon interaction. So what happens in two words is that when electrons travel, as you raise the temperature, the oscillations of the atomic lattice become wider, and therefore there is more scattering. Okay. Another example that actually is under our eyes every day is the use of solar cells like this silicon solar panels that you see in every rooftop these days. And here maybe the connection to electron-phonon physics is not obvious to everybody, but you may become obvious if you look at this diagram here. So this is the absorption coefficient, or light absorption coefficient, versus photon energy. And solar light is essentially on the left, mostly on the left of this of the visible spectrum, and a little bit on the visible. So for a solar cell to function, you need essentially absorption in this range below 3 electron volts. Now it turns out that silicon is a semiconductor with a direct gap of 3 electron volts approximately, meaning that photons alone cannot be absorbed in silicon. So to absorb light, it is necessary for a photon to be accompanied by a phonon in what is called a phonon-assisted optical transition. Okay, so this need that you see from 1 electron volts to 3 electron volts is entirely due to phonon-assisted processes. So if there were no phonons, there would be no absorption in this range. Another property maybe that is a bit more on the fancy side for those who are interested in maybe condensed matter physics things. So this is a measurement of the electronic structure of an oxide called strontium titanate. So what people do with this system is to dope it with electrons by, for example, creating oxygen vacancies, and then measure the electronic energy levels by using photoelectron spectroscopy, meaning one shine lights to a sample and then extract electrons. And from the energy at the momentum of the extract electrons, one can reconstruct essentially the band structure of these compounds. So this is a little bit messy to analyze, but what typically people do in this community is to extract the curvature in this plot, and that's what you see on the right. So the first little parabola, this segment of parabola that I'm pointing at, is essentially the bottom of the conduction band of this oxide. Okay, so imagine taking the conduction on bottom, filling with a few electrons, and that's what you see. So this is the typical picture you will obtain from a calculation based, for example, on density functional theory. But in this experiment, you observe other features like this satellite here, another satellite here, another satellite here, And all of these, if you take a look, they are almost equally split from each other and from the main band. So these things have been called Polaron satellites, and we'll discuss them in a little bit. And then maybe as one last example, so this is probably the most spectacular manifestation of electron-phonon physics, and is the phenomenon of superconductivity. So in a superconductor, what happens is that as you decrease the temperature, it could happen that at some point the electrical resistance goes to exactly zero, and that's essentially the onset of superconductivity and the establishment of a superconducting phase. So in this example, it's a compressed hydrogen sulfide. They cool the sample, down to 195 Kelvin. At this point, you see there is a drop in resistance, and then it stays zero below this temperature. So how do we know that this has to do with phonons? The typical smoking gun is the isotope substitution experiment. So you take this material, this is based on hydrogen, you replace hydrogen by its heavier isotope, deuterium, and that essentially modifies the nuclear mass, and therefore modifies the vibrational frequencies of the lattice, and as a result, we have a change in the critical temperature. Okay, this is a standard way to confirm an effect of superconductivity mediated by phonons. And I'm showing this picture just because a few years ago, this really changed our way of thinking about superconductors, because until then it was thought that phonons can only give rise to very low temperature superconductivity. But this work, and also subsequent works by them and the same authors and others, have shown that now one can reach even room temperature superconductivity using ultra high pressure. So let me now tell you a little bit about the techniques that one uses to study this kind of phenomena. And I want to start from the most general approach that you would see from a community doing electron-phonon physics. And what you are looking at in this slide is essentially is the many-body Schrödinger's equation for a system of interacting electrons and nuclei. So R would refer to the electron coordinates, and tau would refer to atomic coordinates. And as you might expect, there is a kinetic energy for the electrons in right here. Then the inter-electron Coulomb repulsion, so V is the Coulomb potential. Then we have a kinetic energy for all the nuclei in blue, and then inter-nucleus Coulomb repulsion. And then the term in magenta is the Coulomb interaction between electrons and the nuclei. So this is really the most general way you can approach the system, and this is maybe a simplified version because it's non-relativistic, but one can extend it to a relativistic case without too much difficulty. And the problem here is that the wave function now depends on all the electronic coordinates and all the nuclear coordinates, and that's essentially something that we cannot afford these days. You know that there's been a lot of discussion about the electronic problem during this workshop. So imagine now adding on top of that difficulty the challenge of describing also nuclei, and remember that the nuclei have much narrower wave functions than the electrons. So this would be a really very large many-body problem with, in addition, a multi-scale complexity coming from the fact that the nuclei and the electrons have different kind of spatial extension. So in order to deal with this problem, so what one does usually is to try to rewrite the whole problem into single particle equations. And I'm going to show you a few kind of steps, elementary steps to get there, just to give you an idea of how people think in this area. So first of all, what we would like to do is to talk about slated determinants. So imagine a DFT calculation. You have Polarons orbitals. You can do a single slated determinant based on that. It will be obviously approximate, but that's not the ground state of the system or any excited state. So to define the wave function of the system, one considers a linear combination of slated determinants. It could be, for example, single excitations where you remove an electron from a certain constant state and you add it somewhere else. It could be double excitations, we remove two and then you add two somewhere else, and so on. Okay, so the most general expression of a many-body wave function could be written in these terms. So the goal of the whole kind of techniques that have been described, developed to study electron-phonon physics, is to get rid of the wave functions and these determinants, and do more work on the operators. So what one does is to introduce field operators. I'm sure many of you are familiar with this, but I'm just recapping for some of you who may not be familiar with these techniques. So the field operator essentially is a linear combination of, for example, distraction operators for specific single particle states with coefficients that are given by a, let's say, the value of a single particle wave function at a given time. So that's what we call a field operator. The advantage of using this notation is that some operators of the Hamiltonian I showed you in the previous slide can be rewritten in a much more compact form. For example, if you have one particle operators like an external potential acting on the electronic coordinates, the total potential on all the electronic variables could simply be written as a expectation value of that potential over, essentially these field operators. So that's a very, very compact notation that is useful to make, derivations. So how does the Hamiltonian I showed you earlier read in this with this formalism? In practice, we have a sum of 5 terms: the kinetic parts, and then the Coulomb interaction between electrons and nuclei, electrons, and nuclei. I'm not going to give you all these terms. I just want to show how compact are these terms when you use a field theoretic representation. For example, the interaction between electrons and nuclei is very simply given by the Coulomb potential here, multiplied by the electron density, multiplied by the nuclear density. The only difference with respect to a classical calculation of electrostatic interactions is that these are not functions or position, but they're actually operators. And similarly, the electron-electron interaction is essentially a Coulomb interaction here between 2 electronic charge densities. The only difference now with respect to the previous term is that one has to remove the self-interaction of an electron with itself. And just for clarity, the electron density, for example, can be expressed as a product of a creation and annihilation operator as usual. Okay. So the main advantage of using this notation is that now we're really looking at some basic variables that are these densities or these field operators, and we don't need to worry about describing many electronic and nuclear degrees of freedom. So what one does with this kind of quantities? So typically the quantity of interest in these calculations is the Green's function. For example, in this case, the Green's function for an electron. Let me define it briefly. So this is essentially a function of 2 space-time points, meaning position and time. And it is defined as this scalar product. In this expression, n denotes the, let's say, the many-body ground state. We can talk about the exact ground state, even though we never really have this kind of quantity. But let's imagine an exact ground state. So the first 2 bits on the right essentially indicate a system where an electron has been added to a certain point at a given time on top of this ground state. And now, if you look at what is left on the left, just ignoring the t, this Dix operator, just for simplicity, you will recognize the Hermitian conjugate of what I just written here. In fact, this is simply the same state, but Hermitian conjugate and being evaluated at 2 different, different position, different time. So really, what this Green's function represents is the overlap between a system with an electron at this point in time and the same system, but with the electron at the other point in time. And this is essentially the amplitude for the probability of going from a given space-time point to another space-time point. So this quantity is really the core quantity of all techniques that have to do with electron-phonon physics. And the reason why people are interested in this quantity is that if you perform a Fourier transform from time domain to frequency, and then a Fourier transform from space to basically a reciprocal space, one can prove that the poles of this function correspond to excitation energies of the system. So how much energy you need to remove or to add, for example, electrons. So what does one do with this kind of information? In practice, the main application is to start from the Green's function and use its imaginary part to build essentially a density of states that in this language is called the spectral density function or spectral function. So just to give you an idea of how this works, let me make an example, very elementary example. So let's imagine that we start describing the system using density functional theory. So it means that we have some functional eigenvalues, and each of them corresponds to essentially to a pole of a non-interactive Green's function, and the spectral function in this case will correspond to a sharp Dirac delta function P. Now, if we switch on interactions like electron-phonon interaction, for example, a few things happen. Typically, the spectral function takes a slightly different shape. And in particular, what happens is that first, the peak has moved from its original location. Then the peak has also broadened with respect to this sharp peak. So this means that this particle is no longer infinitely deep, but it will have a finite lifetime. And then there are some incoherent structure here in the top here that usually have to do with the involvement of some kind of bosons. It could be, in this case, phonons, what I would like to discuss, but it could also be plasmons, magnons, or maybe in electron hole pair generation and things like that. So this is the kind of quantity one is after when studying these effects. And once you know this quantity, you can perform many calculations of properties like current transport, superconductivity, and so on. So the question now is how does one calculate this self-energy, this Green's function and then the spectral function? So the idea is actually quite simple. One takes the field operators, writes them in the Heisenberg representation, and then from that you can obtain an equation of motion that it contains, basically leads to this commutator. The Hamiltonian here is the one I showed you in the previous slides. So if you evaluate the commutator here, you will find a very simple Schrödinger-like equation that links the time derivative of your field operator with terms that look very much like what you would find in a Schrödinger equation for a single particle, so kinetic energy, and then this potential that has to do with the Coulomb interaction generated by all the density of all the particles in the system. Now, if you were to only consider the electronic problem, this density would be the density of all the electrons, so the many-body electron density. If you are studying electron-phonon interactions, what happens is that this density also contains the density operator for the nuclei, and that's where the electron-phonon interaction comes from. So once one has the equation of motion for the field operator, one can write an equation of motion for two field operators, very simply, and that leads to an equation of motion for the Green's function. So the equation of motion for the Green's function looks like this, and you can see it's almost like a Schrödinger's equation. Here it's a standard energy plus kinetic part, and this is some kind of potential part. Now the complexity here comes from the fact that this term contains four field operators, so psi, dagger, and the density contains psi, dagger, and psi. So that's actually pretty complicated. And that basically is the origin of the physics of Hartley fault interactions, the necessity for considering two particle Green's functions and higher order correlations. But in addition to this, which is more the domain of the electronic problem or electron correlation studies, inside this expression there is also electron-phonon interaction, because as I said earlier, this density is also the density contains also the density of the nuclei. Okay. So to make a long story short, what people do here at this point is to use a Schrödinger functional derivative technique to rewrite this term as the product of the Green's function and a self-energy. And if you want, this expression is basically a definition of the self-energy. Okay, so we define the self-energy so that this term equals the one I showed in the previous slide. And that probably gives us already a hint that this self-energy will be something pretty complicated. Now, in practice, what happens is that this now self-energy is one of the potentials acting on the system. This other potential here is again a Coulomb interaction with the entire density of the system. And the electron-phonon interaction essentially will exist inside this potential here. And that has to do with the fluctuations of the nuclear density. And inside this self-energy here, and this is something that I'm going to describe in a second. So the goal of, let's say, calculations of electron-phonon physics, in a nutshell, is to try and evaluate this potential here and this self-energy in a way that is both accurate and computationally tractable. So how does the self-energy looks like? So the equations are a little bit kind of, not very pretty to look at, but the diagrammatic representation is very cute. So I'm going to describe it in terms of diagrams. So the self-energy contains three main terms. So one is a GW times term. So it's basically an electron line, which is the Green's function, times the spin-Coulomb interaction multiplied by a vertex. So this is exactly the same term that you see in studies of the electron problem at fixed nuclei. And if you neglect the vertex, for example, you would have the standard GW self-energy. If you want to do something more advanced, obviously you need to look into correlations inside the vertex. Then there is two other terms. One has to do specifically with electron-phonon interaction. So there is a Green's function line here, and then this would be the Phonon-Green's function, the wiggly line. Those are connected by two quantities that are, let's say, electron-phonon vertices. And then there is this gamma again, which is the same vertex as before. This is what we call usually the Fan-Migdal self-energy. Migdal is mostly used in the study of superconductors. The Fan name is mostly used in the study of metals and semiconductors. Then there is a third self-energy, which is usually called the Debye-Waller self-energy. You see, it's a little bit weird because the phonon line goes upon itself. Actually, this is not exactly a self-energy. It is somewhat an anomalous self-energy, which actually comes from the potential term, V thought, that I showed you in the previous slide. So it is a static contribution that has to do with the fact that nuclei fluctuate around their equilibrium positions, and that essentially makes their potential a little bit fuzzy. Okay, so all of these things now can be calculated to some kind of using some approximations, and what basically we do in general, it's either to evaluate these self-energies by neglecting the vertex, or trying to incorporate some of these vertex, using cumulant expansions, for example. So what I would like to do now is to show you some examples of applications of this formalism, and then I will tell you more about the practical details, and then I will move on to a problem that we're working on lately, that is the problem of electron localization. So this is the first example, and it's an application to a material that is of interest for solar photovoltaics. So this is the basically ball and stick model of this material. It's called metal ammonium triiodide. It's something of a hybrid between a solid and a kind of organic and an inorganic solid, because the scaffold here has to do with the lead and iodine, like an inorganic compound. But inside you find some molecules which make it somewhat organic, and that creates a lot of complexity in calculations. So so this system is actually mostly famous because it enables the solar cells with very high efficiency. So a lot of experimentalists are working on this now. And one of the questions that is still being debated is what is the role of phonons in the photophysical properties of this compound. So what you see in the middle here is a calculation of the spectral density function for this system resolved into momentum. So if you want, this is you can think of this as a many-body band structure, where the many-body aspect is the incorporation of electron-phonon interactions. The level of theory for the electronic part is simply density functional theory, so there is nothing advanced going on the side of electrons. So the way this is to be read is that the dashed blue line here that I'm pointing out is the initial dispersion. So a DFT band structure you may calculate with any electronic structure code, and the kind of shade, the purple and yellow plot is a spectral density function obtained using this Fan-Migdal self-energy I just mentioned. So if you trace the maximum of this spectral density, you have this black line, which is the new renormalized band structure. So the main effect is that the curvature has decreased, and therefore you have a heavier carriers, so heavier electrons, heavier holes. This can be quantified by looking at how much heavier your mass will be after electron-phonon interactions are taken into account, and the values are in the order of 20 to 40% at very low temperature, depending on the technique used to perform the calculation. The other thing you observe is that the band structures are very sharp when you look at low energy near the conduction and valence band extrema, but they become quite broad as you exceed some kind of threshold energy. So what is happening here is that the electrons are able to emit phonons, and because of that, they acquire a finite lifetime. And one can monitor this kind of lifetime, and in this case, this means that the electrons in this region are only live only for maybe 20 femtoseconds until they decay into some states at lower energy. So this is the kind of things one can do to analyze band structures after incorporating electron-phonon interactions. Let me show you another mechanism, another property that one can calculate. So this is for a system that is much simpler. It's a very simple rock salt structure like sodium chloride, like kitchen salt, from each other. So this is europium oxide, and this is a system of interest in spintronics because it is essentially the only system that is a semiconductor, and it is at the same time fully spin polarized. Meaning, if you look at the band structure, so here blue means, let's say, spin up. The conduction band bottom and the valence band top are both having the same spin. So this could act as a perfect spin filter. And this has been realized experimentally, and the only limitation to actual application is that it is only stable in the structure at very low temperature. So now we can analyze the band structure by using photoelectron spectroscopy. So our collaborator Viking did measurements on this. So what you find from photoelectron spectroscopy is that this band here is essentially the one that you see here. Then the top of the valence band here, you can see it here. And then in the system, they also introduced electrons in the conduction band bottom here, but you don't see anything. And this is simply because the density of electrons in the conduction is so much smaller than in the valence that you cannot see any peak. So what these experimentalists did is to remove this part and to enhance the features here. And after you do that, you start seeing the conduction band bottom. So this very dark blob that you see here corresponds to the very bottom of the conduction band system. And this is what you would expect from, let's say, a density functional theory calculation. You see there is nothing else inside the band gap. However, in this experiment, you see, as in the example of strontium titanate, there is another copy of this band here, a satellite, another satellite. Maybe if you look carefully, there is yet another satellite. So and all of these are equally spaced from each other. So this is essentially what people call polaron satellites. So the physics of this corresponds to, having a photoemission experiment where using light, you extract an electron. In the process of extracting an electron, the system can emit or absorb a phonon, and therefore you have also electrons accompanied by a phonon, or two phonons, or three phonons, and so on. So this is essentially correlation effects between electrons and phonons that are not captured by things like density functional theory, for example. So now these things can be calculated using a Green's functions formalism, and in particular, this is a comparison between what we calculate on the right and what was measured. So this is a calculation done approximately under the same conditions of the experiment, and this plot at the bottom are cuts of this spectral density in the near the center of the spectral and the shapes. So you will see here a main peak that is what we will call the band, or the quasi-particle peak, and then a first satellite, a second satellite, another satellite. And this is our calculation where, again, you see a first quasi-particle peak, and then there are these satellites that correspond to the emission or absorption of phonons, okay? And just for the expert in the audience, so this was done with a slightly more complex technique than what I described earlier. It's called the cumulant expansion, and essentially it's a way to incorporate a little bit of the vertex that I mentioned when I showed the diagrams for the self-energies. One last example I want to give you about these applications is not on the side of the electrons, but on the side of the phonons. So when we talk about electron-phonon interactions, the attention usually is on electrons. So one that asks how phonons do affect the properties of electrons, but one can ask the opposite question: how electrons do alter the properties of phonons. And to show this, to illustrate this, I want to use the example of diamond. So diamond is a perfect insulator, but what happens is that if you replace some of the carbon atoms by boron, effectively, since boron has 3 electrons instead of 4, you reduce the number of electrons. So you are performing whole doping of this compound. So that means that the Fermi level is moving down from the valence band top. And what happens in this case is the phonon dispersion, these blue lines here, become a little bit softer, so the phonon frequencies decreases, and this is a consequence of the fact that now there is a Fermi surface in this material, very small Fermi surface, that introduces some metallic screening in the compound, and this metallic screening is felt by the phonons here. This is a calculation done essentially with density functional theory by changing the number of electrons per unit cell. The problem with this calculation is that the phonon softening for this doping density is about 20 millielectromoles. But if one looks at the experiment, so these are inelastic X-ray scattering experiments, So for the same doping level, the softening is of the order of a few millivolts at most. Okay, so clearly there is some kind of failure of density functional theory to capture this. So in order to do a better job, essentially, one can go back to the formalism I discussed and can perform the same analysis for the phonons. So essentially study how the phonon-Green's function is affected by electron-phonon self-energy. And this leads to also a similar kind of concept where you can calculate self-energies and spectral functions for phonons. And the result in this example looks like this. So this is the undoped system in experiment, and this is the corresponding calculation. This is slightly doped, and you see that there is a little bit of softening and broadening of the lines. And the same is happening here in the calculations. And then this is the most basically highly doped sample where there's a significant bending here. And there is also a loss of spectral intensity near the center of the Brillouin zone. And that's exactly what we see in the calculations. So there is a significant bending, broadening of the phonon lines, and also here we lose signal. Okay, so this is just to give you an idea of the fact that this kind of Green's functional language in self-energies is actually quite powerful and can be used to really describe real experiments with quite some precision. So now I would like to tell you a little bit more about some of the details of these calculations and just explain what is the main challenge as of now. So what we try to do in these calculations is to evaluate self-energies most often. And in the simplest form, let's say we have a self-energy looking like that with an electron line, a phonon line, and two matrix elements. So the matrix element is essentially the most expensive thing to calculate. And it looks as follows. It's essentially a complex number and is obtained as the sandwich between the initial electronic state here, the final electronic state here, and then the change of the potential in the system resulting from a phonon that has been displaced. And all of these things are usually evaluated using density functional theory. Okay, so one doesn't usually go further than that because already things are very complicated at this stage. So calculating electron wave functions, in DFT now it's pretty straightforward. That's not expensive at all. The complexity is in the evaluation of this quantity. So let me explain how this, so what is this made of. So to evaluate the change of the potential coming from phonons, what one does conceptually is to modify the potential by displacing one atom at a time. Okay, so this is the change of the, let's say, constant potential when you move an atom. Once you move an atom, you do that for every atom, and then you decide on a collective displacement by multiplying this by the phonon polarization vector. Then you decide how far are you going to move things, and this is given by the 0-point amplitude. Okay, that gives you a metric of length. And then you need to combine this in a linear combination that introduces essentially a wave in the system and makes it a block function. So the difficult part, the expensive part of this evaluation is that these derivatives essentially require for each wave vector and for each phonon mode a separate density function theory minimization. So this can become quite expensive. So why this is expensive? Because one could say, okay, this may take a few minutes on a laptop. So why should I worry about this? So the reason is that actually in most of these calculations, the number of matrix elements that we need to evaluate these quantities is enormous. Okay, and to explain this point in a pictorial way, I want to use an example that is the one of electron lifetimes. Okay, so let's assume I want to calculate the lifetime of an electron at a given block wave vector. And if you want, without thinking about any kind of complicated formalism, let's say this is just a Fermi golden rule where we have a transition probability here, matrix element square, times a Dirac delta function that takes care of energy conservation between the initial state and the final state that corresponds to the electron down to another, let's say, constant state, plus phonon energy or minus a phonon energy. After a phonon has been emitted or absorbed. Okay, so what is happening here essentially is that I need to perform an integral over all possible phonon wave vectors, but this integral really only contains states that fulfill this relation. All right, so this is a volumetric integral, but when I impose this constraint, I'm really looking at a surface, essentially a 2D kind of component, a 2D subsystem in a way. So let me show you what happens if you try to do this with by discretizing this integral using a few points in the Brillouin zone. Suppose that we want to perform a calculation of this integral using 4 points by 4 points in this two-dimensional example. And this is actually not too far from what people would do in DFT. In DFT calculation for standard systems, you would use maybe 10 by 10 points, maybe 20 by 20 if you are really accurate. But that's the kind of size of discretization. So what would happen basically is that if I had, for example, parabolic dispersions, I would expect this to define essentially a circle, but I find something looking more like a square because of this very coarse, very poor discretization. And then that means that I'm considering only scattering events, for example, from the red points, the blue points, that are not descriptive of what really the system should be. So if I use a much finer sampling, what is going to happen is that my set of allowed points looks more like what I expect, which should be a circle in this example of a parabolic dispersions, and this would have the correct shape of the free space that I want to explore. So this really means that doing calculation using a sampling like on the left is essentially a no-go because you will get the physics wrong, and one always has to use a very fine sampling of the Brillouin zone. So one could ask, okay, why is this a problem? Well, it is a problem because the size of the sampling is typically of the order of maybe 100 by 100 by 100 or 200 by 200, 200, okay, for the simple systems. And you need to consider that this number of points also has to be multiplied by the number of bands here, the number of bands here, and the number of phonon nodes. So to make a long story short, the number of evaluation of the matrix elements leads to an amount of data that usually corresponds to something of the order of 10 to 50 terabytes. And as you can imagine, that poses a challenge in actual calculations. So to handle this, what we've been doing for many years now is to change the representation of the electrons and phonons, going from block functions to one-year functions. So if you've never seen one-year functions, I'll try to explain it in one slide. And the concept is very, very simple. If you take a crystal and you have block waves, usually you can recognize some, so imagine that these boxes are the unit cells. Usually you can recognize some kind of atomic features that are then modulated by some kind of plane wave. So you can imagine that if you make linear combinations of many of those, you might be able to extract these atomic features as localized objects. So this is a very rough way to say that it is possible to perform linear combinations of block waves that will give you localized functions. The way this is done in practice is to take block waves, perform unitary rotations, and then add some phase factors, and this will give you some objects that are called one-year functions. So in this work, the authors, at the bottom, the authors review the whole theory of one-year functions, and this is the team that essentially exploited the gauge arbitrariness that you find in these unitary matrices to obtain one-year functions that are as localized as possible. So these are called the maximally localized one-year functions. So what we did basically is to ask ourselves whether we could exploit this concept to make electron-phonon calculations easier. And that's basically what we've done in the past few years. So the idea is very simple. If you take a matrix element and you write it in a one-year representation, you might be able to end up with a situation where the bra of your matrix element is a localized function here, the ket is a localized function here, and the thing in the middle is also a localized function that is, for example, the dipole potential coming from an atomic displacement. So this concept is important because you can imagine from this figure that if these three objects are sitting far away from each other, then the matrix element will be vanishing and probably you don't need to calculate it. So this very rough concept actually can be formalized essentially in a Fourier interpolation method, where you can write the matrix element in the block representation as a linear combination of matrix elements in the one-year representation. And the idea is that we only need a few matrix elements in this representation to obtain information over the entire Brillouin zone. And this is a dramatic computational saving, okay? So obviously, this idea relies on the notion that the matrix element must be localized. So let me show you how localized they are. This actually is an example that I calculated 15 years ago. So this was the very first calculation we did in this area. And that's basically the size of the matrix element as the two one-year functions at the two ends get farther away from each other. And you can see in this log plot that essentially the decay is exponential. And this is a consequence of the exponential localization of wave functions. So how this works in practice, what happens is that we can evaluate, for example, matrix 7 on an extremely coarse grid, and then we use the formula I showed you in the previous slide to obtain information on the entire Brillouin zone with the same accuracy of a full DFT or density function perturbation theory calculation. And this is a tremendous computational saving, and this is what actually enables many of these calculations of electron-phonon interactions. So just for completeness, let me just show you a more recent benchmark where we were interested in checking how localized are these objects for many systems. So this is an array of semiconductors, and these are just examples for of wave functions, for you to have an idea of how they look. For example, these things look like standard sp3 bonding orbitals. And if you look at the matrix element, the dark purple here, they're all exponentially localized. So they all correspond to wave functions in the valence band. You see that instead, if you look at the conduction band, these things here are not exponentially localized. They're only polynomially localized. This actually is a consequence of the fact that wave functions in the conduction band are much more difficult to localize, and there is no proof that they can be exponentially localized. So there is actually a theoretical challenge that has to do with the localization when you are in the conduction band manifold. So how are these calculations done? In practice, what we do is to do them with a software called EPW that we developed in our group and with several collaborators. So this is something that started 15 years ago, actually more than that, maybe 17 years ago, and we keep improving it and trying to make it more, kind of user-friendly for others to use it. So the way this works is that this code takes density function perturbation theory information from quantum espresso, takes information about 1A localization from 1A90, and then processes this to evaluate a number of properties like maybe superconductivity, band structure normalization, carrier transport, phonon dispersion relations, and so on. Using this Brillouin function formulas that I try to recap very briefly earlier. So the way the development of this code works is that we are now a few groups working on it. So there is us at Austin, the collaborators in Michigan and in New York State, so people in London, in France, and in Belgium. So now this is really becoming something that goes beyond our group, really, and each of these partners is really focusing on one specific aspect of electron-phonon physics and trying to develop specific modules of this package. And just to give you an idea of where we are in terms of kind of computational improvements, we've been investing a lot of effort in the past maybe 2 years now to enable this code for exascale computing. So this is the result of some scaling tests that were performed by Yoon Jun Lee at UT, where basically we managed to get hold of the entire Frontera supercomputer at the Texas Advanced Computing Center. So that's a 40 petaflop machine is essentially 500,000 Skylake cores, and the code scales up to maybe 86% of the ideal speed up in strong scaling test. So that's actually very promising because it means that we can use the entire machine. And now there are new results where this has also improved, and we keep trying to push it higher and higher to make sure that we will be ready for the exascale transition that is happening in the US. And finally, if I have maybe let me check if I have another maybe 8 minutes, I will tell you a little bit about Polarons. So this is an activity that we've been kind of pushing in the past maybe 5 years, and where there is a lot of work to do, and we are finding a lot of new physics and new theory to play with. So it's a very interesting playground, and I just want to give you a flavor of what this is about. So I assume that everybody at some point in their life heard about Polarons. So these are the intuitive notion is that you take an insulator, a material, you add an electron, and if the electron-phonon interaction is strong enough, the electron may drag some atoms around itself, and then these atoms will actually pin the electron at their location, forming essentially a Lamport charge that is a combined electron plus atomic displacement unit, and this acts in a way that is quite different from standard electrons. So if you're interested in this kind of physics, there is a very nice review by Cesare Franchini from last year, where they really essentially looked at the state of the art in terms of experiment and theory in this area. And for me, the main interest in this area is that the notion of localization is really interesting because as condensed matter physicists, we've been trained to think in terms of delocalized block waves. But if a picture like that exists and really we can calculate it, maybe that would lead to a change in perspective in the way we deal with solids. So let me try to explain what is the basic idea here with a cartoon. So the idea is that you start from an insulator, maybe a semiconductor, where you have filled valence band and empty conduction bands. So the dots will be atoms, and then this is the potential coming from the atom. So everything is periodic. Then we add an electron, and we minimize, for example, using density functional theory. So the electron will go to the bottom of the conduction band, and because of that, it is a delocalized block wave. But what if, instead of finding this picture, our calculation gave us something looking like this, where the electron localizes, the atoms also gather around the electron, and now you have a state in the band. So is this possible? Can one engineer something like this in the calculations? How do they relate to experiments? So to explain how this process works, I just want to use a very simple model that has been very instructive for us and that where we learn a lot, actually. And this is the Landau-Pekar equation. It is an extremely simplified model of this phenomenal localization that is, contains a lot of the physics that we want to address. So in this model, essentially, one considers a dielectric continuum. Imagine a material which is uniform and is defined by a single dielectric constant. And then you add an electron with a certain wave function psi that you describe quantum mechanically. So their idea here was to write the energy as the sum of a kinetic part with this electron and the electrostatic energy of the field that is interacting with the electron. So how do we proceed from this? The idea is that the divergence of the displacement field relates to the density of free charges, so you have to relate to this electron. And then the divergence also relates to the electric field via the dielectric constant. So if you combine these expressions and you place them in this integral, you obtain an expression for this energy that is as functional of the electron wave function only. So this is essentially an interaction of the electron with the lattice, but written only in terms of the electron. And as you can see, that's the shape of some kind of a half-tree interaction. So how does this thing look like? So to give you an idea of how it works, let me use a very simple variation of ansatz. I'm going to replace the wave function by a decaying exponential with a given radius. So I replace this exponential. And what you find is that if you evaluate the integrals, it can be done by hand. You obtain a first term, that is the kinetic part in blue. Second term is the interaction with the lattice in red. The most important observation is that the first term goes as 1 over the size of the wave function, the size square. And the second term goes as 1 over the size, and it has a negative sign. So when you try to represent them in this plot as a function of radius of the wave function, you have the blue term is the kinetic energy. Essentially, it is favoring delocalization. The red term is the Coulomb part that favors localization. Since they tend to infinity with different kind of powers, there will always be a minimum, and this minimum is more stable than the fully delocalized solution. So in this very simple model, you always have some form of localization, and that depends on the dielectric scale in the system and on the effective mass. So what we wanted to do here is to understand whether this kind of physics is contained in something like density functional theory. Problem is, in DFT there is a little bit of a complication, because as you know very well, there is something called self-interaction error that essentially will add to this expression and will tend to delocalize the electron wave function. So what we did is to essentially try to work out a formalism that starts from DFT, removes the self-interaction using a self-interaction correctly, and enables the use of a language of phonons. To do that, essentially, we truncated all the expressions of DFT total energy functional to second order in the atomic displacements. Okay, so U here would be atomic displacements, C would be the interatomic force constants, and psi would be the wave function of the electron that we have added. So this energy in this case would be the formation energy of the polaron, meaning the difference between the energy of the system with an extra electron and the energy of the system without this extra electron. So this is, in practice, is a system, an energy that is a functional of this electron wave function, atomic displacement. When you have a functional, you want to look for an energy minima, so you take a functional derivative, and this leads to a couple of equations that where the first one looks a lot like standard Computational equation, except that there's an extra term that depends on the atomic displacement. And the second equation gives you the displacement in terms of the electron density. So this is something that one can solve in principle and try to see whether there are stable solutions that are not localized, not delocalized. The challenge is that your polaron may be spanning 2, 3, 4 nanometers, and in that case, you may need the supercells that contain something of the order of 10, 20, 30,000 atoms. That's very difficult, of course, using the FT. So what we need here is to observe that this wave function and these displacements can be represented in a basis of block states, because those block states form a continuous basis, sorry, a complete basis. So instead of trying to solve for this in real space, we write them as linear combination of block wave functions with some coefficients here, and the same for atomic displacement, written as linear combination of Phonon polarizations, and you see the coefficients here. So this is very similar to what people do in the study of excitons using the Beres-Peter formula, where you write the correlated electron hole wave function as a linear combination of products of conduction and valence states. So if you do this now, the system I showed you in the previous slide becomes a much more compact expression where you have these coefficients A and B, that are the solutions, and the ingredients are simply the electron band structures, the Phonon dispersion relations, and the electron-phonon matrix elements. So this quantity is something we can calculate very easily, as I tried to explain earlier, and therefore this is all well defined, and one can perform calculations of this and check if you have states that are more stable than your standard solutions. So this is an example of an electron added to lithium fluoride, which is a standard, rock salt kind of alkali halide insulator. And what this calculation corresponds to is to take this with completely filled valence bands and add one electron to the conduction band. If you were doing a DFT calculation, you would have a fully delocalized wave that is completely periodic. But using this technique, you see that the electron actually wants to localize and form essentially a Lampo charge. In this case, the localization actually is over maybe 12, 13 unit cells. So this is what we call a large polaron. You can do the opposite operation and remove an electron from the system. So you look for whole polarons. In this case, it's quite interesting because the length scales change completely. So instead of having something spanning, 12 or 13 unit cells, this is spanning only a couple of unit cells. So it's almost like an atomic orbital. In fact, this is the combination of two atomic orbitals in the system. So this is what we call a small pole polaron. And I think this here I want to connect to what I was trying to say earlier. That you need to think that when we remove electrons from the valence band of an insulator, we usually have in mind this density functional theory picture where everything is delocalized, so we can talk about block waves. But here, what I'm showing is that this object is what you really find if you remove an electron, and this is more stable than the delocalized solution. So this is actually quite interesting to us because it means that maybe we need to start thinking about a new perspective on how to deal with electron addition or removal from solids after taking into account these electron-phonon interactions. So just to give you an idea of how stable these things are, in practice, if you remove an electron from the valence and then you let the atoms relax around it, you gain 2 electron moles. So these are gigantic change of the kind of energetics, and we believe that this has to be taken into account when discussing band gaps and other properties of many insulators. So now we are doing more work trying to understand, the impact of this kind of localization on a number of other systems. And I think I'm exhausting my time, so I'm just going to put a kind of a summary slide here to say that I try to explain that what we are looking at is a number of phenomena related to phonon-electron interactions, from band structure normalization to normalization of phonon dispersions to satellite features that one finds in photoelectron experiments, and also phenomena of localization. And I think as a concluding message, I would like to say that so in the era of electron-phonon physics, this is, I think all these ab initio calculations are really much more recent than a lot of the work that's been happening in the electron correlation problem. So I'm sure there is a lot of very nice theory that is still left to discover in this area. And I really would like to encourage some of you who are really kind of experts in the electron problem to maybe look at the open problems in this area and see whether some of the techniques that you developed may be used also in this context. And with that, I would like to just close and acknowledge the group in Austin and say that many of the slides that I presented are actually from a group of former students and postdocs. Some of them have moved on now, are already professors in some other universities. You see the list here. And also, we'd like to say that our sponsors currently are the Department of Energy and the National Science Foundation. So this is the end of my talk, and I'm happy to take questions.